chapter. All right, well, let's begin chapter 8, section 2, electrolytes and non-electrolytes. When a substance conducts electricity when dissolved in water, it is considered to be an electrolyte. Ionic solids, ionic salts built of ions are considered to be electrolytes. A substance that does not conduct an electrical current when it's dissolved in water is called a non-electrolyte. They stay as neutral molecules. So molecular compounds are considered to be non-electrolytes. Now let's just review a little bit. Remember how these are built of a nonmetal plus a nonmetal covalently bonded? Covalently bonded. That means they're sharing electrons. There's no such thing as ions in a covalent molecule. And therefore, since there's no charged particles, it would not be a conductor of current. For example, glucose or table sugar, blood sugar, C6H12O6, since this is a molecular compound, all nonmetals, I don't see any charged species in here. This is going to be a non-electrolyte. Another example, hydrogen peroxide. Hydrogen peroxide does not dissociate. It is not built of ions, because all of these are molecular compounds, nonmetal to nonmetal, sharing electrons. So it is a non-electrolyte. But when you consider an example such as table salt, NaCl, as a solid, we see that it's in a regular crystalline form. But when you place it into water, it dissociates, it separates, it breaks apart and forms ions. So just think about what we're saying. When NaCl as a solid is placed into water, the ions separate from one another. You get an aqueous ion of sodium +1 and an aqueous ion of chloride -1. These are considered to be electrolytes because they're built of charges, and an electrical current is really nothing more than a flow of electrons. And a flow of electrons simply come from charged ions. So to recognize electrolytes, look for ionic salts. To recognize non-electrolytes, look for molecular compounds, those guys that are built of nonmetals covalently bonded. Now don't confuse this with does it dissolve, because both of these dissolve readily in water. But the idea is, will it conduct a current when doing so? If it does, it must be built of ions, charged atoms. Electrolytes, in terms of classification, can be broken down into two different areas, two different categories, called strong electrolytes and weak electrolytes, and then we'll talk about non-electrolytes as well. A strong electrolyte dissociates completely in water to form ions. Some examples of strong electrolytes would include sodium chloride, potassium hydroxide, hydrogen chloride, potassium bromide. Let me give you an example of what I'm saying in terms of the dissociation arrow. So an example of strong electrolytes, which means they 100% dissociate. And if you don't like the word dissociate, think of it as separating, breaking apart. When sodium chloride as a solid is placed into water, we form 100% an aqueous ion of sodium and an aqueous ion of chloride. When potassium hydroxide is taken out of the bottle, it's a white crystalline solid. When I take that and dissolve it into water, the ions will separate into an aqueous potassium ion and an aqueous hydroxide ion. Now remember, the polyatomic ions stay together. Polyatomic ions, we have a chart of those, don't we? They're groups of atoms acting as a unit carrying a charge. So hydroxide is one unit carrying a -1 charge. One more example, potassium bromide. As a solid coming out of the jar, this one is kind of a reddish salt. I take it and dissolve it into water. Out comes an aqueous ion of potassium and an aqueous ion of bromide, AQ. All of those 100% will dissociate. When I consider now an example of a weak electrolyte, they only partially ionize or partially dissociate or partially separate. And let me give you an example there. Weak electrolytes include ammonia, acetic acid, hydrofluoric acid. Let's take, for example, acetic acid, CH3, CO2H. When it's dissolved into water, we set up an equilibrium where really only about 1% of the molecule dissociates and 99% of it stays in the molecular form. A little bit of aqueous ion of hydrogen and a little bit of the acetate ion, both aqueous. Ions are always aqueous. There we go. Notice that I'm setting up an equilibrium arrow to designate the weak electrolyte, that the vast majority of the equilibrium lies on the left, the put together molecular form. So when we see a partial ionization, the molecule is not very good at separating, but it will just a little bit. And then a non-electrolyte, such as, we had hydrogen peroxide, H2O2, it will not separate at all, so no ions form. It's not built of ions at all to have any dissociation. So here we have some examples of strong electrolytes, 100% separate into aqueous ions. Weak electrolytes that just partially dissociate into aqueous ions, and the non-electrolytes that are not built of ions at all and therefore cannot separate. We've distinguished between strong, weak, and non-electrolytes and have provided examples of each. What do you think about this? Let's classify as strong, weak, or non-electrolytes. Pause the video and see what you think. Put an answer down and come back when you're ready to check. Well, let's share some strategies. In our first picture, I noticed that I have some red and blue atoms in molecular form, noticing that those are non-dissociated, those are molecules. So how about if I just called that compound AB? And then I do notice that some of them are separated into A's and B's. So we have a separated red and a separated blue, all in a mixture of both. Since both are present, since the molecular form, which are bonded, and the ionic form, which were separated, are both present, I classified this as a weak electrolyte. I notice in picture B, all I have is the bonded form of this compound, that I don't have any separation at all, so I called this a non-electrolyte. And in letter C, notice that they're all separated. Since they're all separated, you have only what I'm calling A positive and B negative, 100% of those dissociated, that must be a strong electrolyte. Did you get those? I bet you did. How about the following example? Would these solutions be electrolytes or non-electrolytes? Now, I want you to remember, electrolyte, these are ionic salts. I need to find a metal positive ion hooked to a non-metal anion, right? These are cations bonded to anions based on opposite charges. Non-electrolytes are molecular compounds. They're not built of metals and nonmetals. These are the nonmetals all bound together in covalent bonds. So letter A, KCl. If I put KCl and dissolve it into water, out comes an aqueous ion of potassium and an aqueous ion of chloride. This is a strong electrolyte. All water-soluble salts are strong electrolytes. Well, here we have C12, H22O11. When I place this into water, there are no ions to separate. This is a non-electrolyte. It is not built of ions. So therefore, there's no separation into aqueous ions at all. It is what we call a molecular compound, built of all nonmetals. Therefore, there's no such thing as charges. And letter C. Well, this is potassium iodide. That is a metal and a nonmetal. It's a salt. It is a water-soluble salt, so 100% of it will dissociate, which means to separate, and form aqueous ions. It is a strong electrolyte. The trick is to just notice that when you have a metal to a nonmetal, it's called a salt. Built of ions will conduct a current when they dissociate, which means to separate and form ions. This is a term, equivalence. It's often used in the healthcare professions. You will hear this all the time in a laboratory setting or distributing meds and so forth. An equivalent is defined as the number of moles of charge that a mole of ion contributes to a solution. The number of moles of ions in a solution. So the number of equivalents per mole of an ion equals the charge on the ion. Now that is worth highlighting. The number of equivalents per mole of an ion equals the charge on the ion. Now, sometimes we have positive charge and sometimes we have negative charge. And in solutions, there must be an electrical balance. So you have to have a balance between the total positive and the total negative charge. Just like in an ionic salt, we need one positive charge to balance one negative charge to create an electrically neutral solution. For example, this is the calcium ion, Ca2 positive. Because the charge is 2 plus, calcium ion contains 2 equivalents. Remember, the equivalents are equal to the charge on the ion. Whereas if I see potassium, notice it has just a +1 charge. Therefore, we see it has just 1 equivalent. The equivalence is equal to the charge on the ion. So if you take a look at this example, just a table from your book, notice that in the first, I'm given sodium ion, Na+1. We're given calcium ion, Ca+2. a bicarbonate ion, HCO3-1, and a phosphate ion, PO4-3. When you're asked for the equivalents delivered from every mole of ion, Na+1 delivers 1 equivalent. Ca2 positive delivers 2 equivalents. The bicarbonate ion delivers 1 equivalence, and a phosphate ion delivers 3 equivalents. The equivalence is a unit that tells us the charge delivered per mole of the ion. Well, let's try one, shall we? How many equivalents of sulfate ions are present in a solution that contains 3.2 moles of sulfate ions? If you don't have these memorized yet, which you don't have to, but you do have to know where to find this information, pull out your polyatomic ion chart. It's a test-taking tool page that you've printed off and you use regularly when formula writing, and it's provided for you on any quiz or test. The more that you get familiar with the chart, the less you rely on it, but I'm not forcing you to memorize, but you do have to know how to use the tool. What is the formula for a sulfate ion? Well, I want you to notice the ATE tells me it's a polyatomic ion. And when you find sulfate, you see that it's an SO4 and it carries a -2 charge. Now, if you can't find the sulfate polyatomic ion on your chart, you're going to be in a world of hurt right here. So commit to knowing how to use your tools. This is the key piece of information. That tells me that there are 2 equivalents in every 1 mole of sulfate. The SO4-2 tells me 2 equivalents are delivered from sulfate for every 1 mole of the sulfate polyatomic ion. And so if we have 3.2 moles of it, how many equivalents will we have? Notice what I've done is just canceled the mole unit and brought it back to the number of equivalents. 3.2 doubled is 6.4 equivalents. And I'm just going to abbreviate that as equivalents is what you'll hear then. That's easy. The hardest part was trying to find the polyatomic ion chart, I would imagine. Why don't you pause and work these out? Come back when you would like to check your answers. Using the given number of moles, calculate the number of equivalents of each ion present. So again, the key is knowing that the charge tells you the equivalents per mole. So the information you need is provided. I didn't even need to go to my chart or periodic table. The information provided me because the charge is given in the problem. I have 1 mole of Na+, and I know based on the number of equivalents, the charge is 1. So there's 1 equivalent in every 1 mole. So you would have 1 equivalent. Moles canceled, and you have the number of equivalents. In letter B, we're given 1 mole of magnesium, which is 2 positive, which tells me that there are 2 equivalents in every 1 mole. So that would deliver 2 equivalents. Piece of cake, right? 0.5 moles of potassium. Whoops. What I know from the formula is that there is 1 equivalent delivered for every 1 mole of potassium ion. Just to put the labels in there. So this would deliver 0.5 equivalents. And the last one, 0.5 moles of the phosphate polyatomic ion. Well, clearly you see that there are 3 equivalents delivered for every 1 mole of your phosphate polyatomic ion. This would give us 1.5 equivalents, which is 3 times 0.5. we've determined how many equivalents of each ion are present when provided the moles of each charged species. These are all examples of electrolytes. The amount of an electrolyte in blood plasma and IV solutions is often reported in the number of milliequivalents per liter of solution. That is a very familiar term, milliequivalents per liter. If I highlight that, you'll commit it to memory, correct? Milliequivalents per liter. It's most often used in the healthcare profession. Remember, in a solution, there must be a balance between the total positive and the total negative charge of all the ions present. Just like when we're writing formulas, the positives must be electrically balanced by the negatives. If a solution of potassium chloride contains 40 milliequivalents of potassium ions, it also contains 40 milliequivalents per liter of chloride ions. They are balanced in electrolytic solutions. Let's try a question out with that thought in mind. If an intravenous aqueous sodium chloride solution contains 154 milliequivalents per liter of sodium ion, that's a given quantity, 154 milliequivalents per liter of sodium ions. How many milliequivalents of sodium is a patient given in 800 milliliters of solution? Well, this is really just a canceling of units as well, isn't it? I want to get rid of the liter, so I'm going to multiply by the liter, and when I do that, I can cancel the liter out, and I could just say that I can set that over 1, and I've converted then to a milliequivalent. 800 milliliters, notice this decimal, meaning that it has 3 sig figs. And I know that in every 1 liter, there is 1,000 milliliters. So this is just a simple slide of the decimal, 3 places. Make sure that you still report 3 sig figs in your answer here as well. So I have 0.800 liters of solution. How many milliequivalents am I delivering? Well, if 1 liter delivers 154, 154 times 0.8, I would be delivering 123.2, and I'll remember to report 3 sig figs in my final answer. If 154 milliequivalents of sodium are delivered for every 1 liter, how many would be delivered if I had 0.8 liters? And I simply cross multiply, the liters canceled, and I would deliver 123 milliequivalents of the sodium ion in that given to that patient. Shall we try another? We have a potassium chloride solution given intravenously to a patient that has a low potassium level. It contains 40, 2 sig figs, that's the decimal point, milliequivalents of potassium in every 1 liter of solution. That's the number that I'm given right here. How many milliequivalents are present in 550 mils of solution? Well, to get the liters to cancel, I have to have liters that I multiply by. So we're just emphasizing that I need like units. 1 liter is equivalent to 1,000 milliliters. So we're simply sliding the decimal place 3 spots to the left to convert milli into a liter. And this problem then is very similar to the previous problem. If 40 milliequivalents are delivered in every 1 liter, 40 times 0.55 gives me 22 milliequivalents. Notice the liters have canceled and you've converted to a milli equivalent. Here we had 2 sig figs, so my answer will have 2 sig figs. Try this one on your own, pausing the video, work it out, come back when you're ready to check. All right, well, let's see what we did. We have a solution that contains 15 milliequivalents of the sodium ion in every liter, and this also contains 10 milliequivalents of the potassium ion in every liter, and we have calcium 4 milliequivalents of a calcium ion in there as well. What is the total number of milliequivalents of the positive charge? Now remember, this is already taking care of the +2. So already, we don't double it. There's 4 milliequivalents of calcium ion already accounted for. So all we really need to do is to sum the total number of milliequivalents found in that solution, right? It's all the same solution, but it's containing 3 different positive charge. So what is the sum? 15 plus 10 is 25, plus 4 more is 29 milliequivalents total in that liter of solution. The total positive is 29 milliequivalents. And if there's only one anion, it's chloride, it must balance all the positive charge. So what does that equal? Well, that's 29. So the 29 milliequivalents of chloride ion are in solution to balance the total positive charge. Remember that wherever we have a positive, we need 1 negative to electrically balance the charge. I like this math. It's nice and easy. If a solution contains 125 milliequivalents of sodium in a liter of solution, how many milliliters of solution are contained in 25 milliequivalents of sodium? Well, this time when we cancel, we want the milliequivalents to cancel out, don't we? And we want to end with the liter. So when we think about setting this up right here, 25, and this is the variable we're solving for, isn't it? So we have to divide by 25. You can think of this really as a ratio, or think of it as a proportion. If 125 milliequivalents of the sodium are delivered in every liter, 25 milliequivalents set over X liters. It's kind of the same scenario of how we'll solve, right? So when I think about solving, 125x equal 25. So what we're trying to do is pull out the volume. Divide both sides by 125, and x will come out to be 25 divided by 125. And I get 0.2 liters. And I'm going to just erase this to make that more clear. Let's erase that and set it up as a ratio or a proportion. So set this up as a proportion and we'll see that equivalency easier. I'm going to say 25 times 1 set equal to 125 times x. That's how we'll cross multiply. And then to solve for x, we see that we divide both sides by 125, and that's how we isolated x. And when we do so, we found our x to come out to 0.2 liters. Notice our question said how many milliliters? And so really, let's continue that thought, because 0.2 liters times, and remember how we said there's 1,000 milliliters in every liter? So you're really just saying 200, move the decimal 3 spots back to make it a milliliter. We need 2 decimal points, don't we? So 200 milliliters with 2 decimal points would be 2.0 times 10, and we would have to say squared to make it 200. Good work. Take a moment and chew on that if you need to. Go back and just tell yourself how we solved for the volume by setting up a ratio, or just simply think of it as a proportion. 125 is to 1 as 25 is to x. Solving for x, we found the volume. Remember, it came out to us in a liter, and so we put it back into a milliliter for our final answer. Let's pause our lessons here, take a little break, come back for your second lesson when ready.